I'm going to go through and sort of as a supplement do a quick little derivation of the 5 kinematics equations in one spatial dimension that we'll be using. Sort of see where they come from and what they mean. I'm going to assume that the time when we start our clocks is 0. And for the kinematics equations, the acceleration is a constant. So it's not changing with time. So we're going to get our first kinematics equation by starting with the acceleration is equal to the rate of change of the velocity, and I am going to go through and integrate both sides of the equation with respect to time. This is why physicists love this notation for calculus instead of the primes to denote differentiation. Instead using differentials. So the acceleration is a constant, so I can bring it out. So I just have the integral of dt is equal to the perfect differential for dv. Therefore, the acceleration times time, because I'm taking t0 to be 0, is equal to final minus initial velocities, v minus v0. And I can clearly rearrange this equation to tell me that v, final velocity, is the initial velocity plus acceleration times time, which that is one of the kinematics equations. Can play a similar game, working towards position as a function of time by starting from velocity is the rate of change of position. And I'm going to play the same game, integrate both sides over with respect to time, but I'm going to plop in that this velocity is equal to v0 plus acceleration times time. So the equation I'm working with is going to look like v0 plus at integrated with respect to time is going to be the integral of dx dt integrated over time. So I'll wind up with a term that's linear in time, v0t, and I'll wind up with a term that's quadratic with time, a half a t squared, after I complete this integral. So that's v0 times time plus a half a t squared. It's going to equal x minus x0, the displacement. And remember that we are picking the initial time to be 0, so that term is dropping out in these equations. Not a big deal if it were there, it's not a big complication. But this tells us that the final position minus the initial position is the initial velocity times time plus a half acceleration times time squared. Okay, so that's 2 kinematics equations that we have worked out. I can play a similar game to derive an equation that looks very much like this one, except it has a minus sign and it's the final velocity, not the initial velocity. So let's see where that comes from. And say the initial velocity is rate of change of position at the initial time. And we're going to go through and integrate both sides with respect to time. But now, since this is v0, I'm substituting in the final velocity minus acceleration times time, integrated with respect to time, and on the right-hand side, dx dt integrated with respect to time. And this is going to give us, very similar to what we had before, final minus initial positions is going to be final velocity times time minus a half a t squared. So there we have three equations of kinematics. And this one is different just because instead of being the final velocity v, we're using the initial velocity, so I have to move this term to the other side. So it comes in as a v minus at. V minus at, all integrated with respect to time. All right. The fourth equation that we're going to derive for kinematics does not really depend on calculus so much, but if the acceleration is constant, that tells me that the velocity is a linear function, and we can look at the average velocity. If the kinematics equations are valid, the average velocity is just a half of the initial and the final velocity. And moving at the average velocity, I move the total distance and the total time. So in terms of average velocity, I can say x minus x0 is the average velocity times time. Substituting what that is, and we have another equation of kinematics. X minus x0 is a half v plus v0 times time. And this is just the displacement in terms of the average velocity. All right, there's one more equation of kinematics, and this is the one I think is actually generally the most useful thing to pull out of your hat and apply in a problem, because it does not involve time at all. So it looks a little weird, but we're going to just start with this construction to get our last equation of kinematics. Final minus initial velocity times final plus initial velocity. And you do your cross multiplication, you realize that that is final squared minus initial squared. And we have expressions for each of these that we've worked out already up to this point. Final minus initial velocity is the acceleration times time, and final plus initial velocity, we just worked out, is twice the displacement over time. So we can set up an equation of kinematics that looks like v squared, final speed squared, minus initial speed squared is going to be a times t times twice the displacement over t, and the t will clearly cancel out. And so we have our last equation of kinematics. V squared minus v0 squared twice the acceleration times x minus x0. There we go. The acceleration is constant. Then these five relationships connecting time, position, velocity, and acceleration are all true.